Good morning. Our topic for today will be the second part of our trigonometric function analysis. Um, this time we're going to analyze what we call a midline, or also called a vertical displacement, in terms of attending the precision and critical thinking skills. But before we proceed with that one, let us consider using RTI 84 calculator. Last time we have done graphing a sine function. This time we're going to graph a cosine function. So make sure that your calculator is on cleared. That's a second plus 712 to clear it. Now to also make sure that on top it says radians. That's the default setting for our calculator anyways. So graphing it, we'll just click on y equals, and then we're simply going to put in the cosine in here. It's beside the sine and the tangent functions, and let's put an x in that case. Sorry for that one. So again, that will be a cosine, and then an x in that case. So we're going to use this x, t, theta, and n. That's beside the alpha, the green button, and then put a parenthesis in there, and we can see the graph of our cosine function in that case. Now, if you want to clearly see it, we can zoom it in by pressing zoom and number 2 and press enter so that we can clearly see it in there. Um, let's now use our Desmos calculator on how to graph this in Desmos. So we are now on Desmos in here. So to graph it, first of all, make sure that our settings should be in radians in that case. And then we're simply going to put in here y is equal to, and then to get our cosine function in this case, we're simply gonna go to our keyboard app in there, and under functions we're gonna go to our cosine in that case and put an x inside. Again, make sure that it is in radians under the settings. After that, we can drag the graph in here, and we can in fact zoom it in so that we can clearly see it in this particular case. So let's analyze our cosine function in this case for now. So in analyzing our y equals cosine x in here, again, make sure that it is in radians. We can see in here that there are the maximum points. So this is the maximum point. This is also another maximum point in here, while this is our minimum point. Okay, so for the maximum point for cosine x is 1, and the minimum point is actually negative 1 for the y values. Also, if we can see the intercepts in here, or what the y intercepts, we can see that it passed through the following. In this case, those are the following in there. So in fact, if this is in radians, we can actually see that at the minimum, in fact, at the minimum in here, that is 3.14 approximately, or pi, and then at the maximum on this case is approximately at 6.28, which is 2 pi. And in here, this is the origin in here, 0, 0. So we can see that the cosine function actually, or cosine x, actually has its minimum at pi and a maximum at 2 pi in that case. Now, in terms of analyzing um, where our period in here is, so the period in here is from the second maximum to the first maximum. So in that case, the period is in fact from here, from here up to there, then that will be in fact 2 pi the period. And as you may see, one complete cycle for a cosine function should look like that in there. Before we summarize our analysis of our cosine function a while ago, we can see in here some of its applications. So the one on top is in fact the time lapse of the sun's path. This is what we call the land of the midnight sun. So you can see this in any Arctic region, but this one is particularly in Norway. But I would say you can also see this one on most probably the northern part of Canada and Alaska in that case. As you may see in there, the path of our uh, sun is in fact in a sinusoidal manner in that case. The one at the bottom, so again, this is the sun's path. The one at the bottom is what we call our acoustics or the study of sound. So as you may see in our sound in here, it basically tells us like the register of sound as like a sinusoidal function in there, and you can see a sound also has its amplitude and frequency and everything else in there that we can see as a sound wave in terms of a sinusoidal function as well. Going back to our analysis of trigonometric function, last time we have dealt with the amplitude and the period. For this time, we're going to deal with what we call the letter D in here, which is what we call the midline, or also called what we call a vertical shift. So meaning whether the sinusoidal function, whether sine function or cosine function, will be translated going up if it's positive or going down if it's negative. Now, the formula for our midline is the following. That's the maximum y value minus the minimum y value all over 2. So as you may see, it's almost similar to our amplitude, but instead of subtracting, we are, in fact, in here, sorry for that, we are adding. So again, the midline, once again, is maximum y plus minimum y all over 2, while the amplitude is maximum y minus minimum y all over 2. In terms of a graph, we can see the midline as always passing through, like in our sine or cosine function, it should always pass through the middle of our curve in there. So again, or wave in there, that's what we call our midline. Also the same if it's a negative sine or a negative cosine function, it will always pass through the middle of the curve. Let us now apply our knowledge of midline and amplitude and also period in some examples in here. We are now on our first example. It says a Ferris wheel has a diameter of 80 feet. Riders enter the Ferris wheel at its lowest point, which is 5 feet above the ground, at time t equals 0 seconds. Now it says one complete rotation takes 65 seconds. Which of the following function models a rider's vertical height at t seconds? So in this case, we'll be particularly concerned about the midline in this case. But if you are concerned with, if you want to be concerned with amplitude and period as well, then you can go back to my previous video about these trigonometric functions. Okay, so analyzing this one, we can actually visualize its path as follows. So it will start in here at the minimum point at t equals 0. It starts at the lowest point, which is 5 feet above the ground. So if we have the ground in here, in that case, then that's the what we call the minimum point in that case. And then after that, the path of the Ferris wheel, as you may see in here, it looks like a negative cosine function, and then it goes down again in here with a 5 feet minimum again. But as we may see in here, we'll consider what the maximum point above there in that case will be. So to get the maximum point, it says that the diameter is in fact 80 feet. So that means from that maximum point to the minimum point in here, that is an 80 feet. So that means this is 80 feet with a 5 feet uh, minimum value in there above the ground. So that means 80 plus 5, then that will be an 85 for the maximum. Obviously in terms of feet. So with that being said, we can now proceed with going to get our midline, or what we call our D value. Then that will be equivalent to the maximum Y plus the minimum Y all over all over 2 in that case. Okay, sorry for that. So with that being said, a maximum Y value is 85 feet plus the minimum Y value is 5 feet all over 2. Therefore, we're going to get 85 plus 5 is 90 all over 2. Then that will be a 45 feet for our midline. So which among these will give us our answer in this case? So again, our formula is y is equal to, in this case, negative a cosine b x plus c plus d. So we're talking about the midline in here, which means that the midline will be a 45 feet value. So that will be letter D in this case. Once again, if you want to consider the amplitude and the period and even the phase shift in here, you can go back to my previous video about trigonometric function, focusing on those two components. Before we go to our second problem, let's verify using our Desmos graph and see how actually a negative cosine function looks like. So as you may see in here, this is where our, or how it looks like our negative cosine function, where it starts at the minimum, goes to the maximum, and goes back to the minimum for its one whole cycle. Let's now go to our second problem in this case. It says, suppose the function h of t is given to be 8.5 sine 0.017t minus 1.35 plus 12. This model the hours of sunlight for a town in Alaska where t equals 1 is the first day of the year. Based on the function, what is the approximate range of daylight hours for the time? So again, when you talk about the range, we're talking about what the minimum and the maximum values are. So with that being said, we can first consider the formula y is equal to a sine bx plus c plus d. And once again, in here, we only have two components in here that has the maximum and the minimum values. And again, that will be the midline, which is our letter D, which is in fact, that's maximum plus minimum for y all over 2. And also our amplitude A in here, which is in fact maximum minus the minimum value over 2. So with that being said, then we can say for our equation, we have the following, that our A, which is in fact 8.5, is equal to maximum minus minimum all over 2. And for our second equation, we're going to use our, so again, that's our first equation in this case. For our second equation, therefore, we're going to use our midline. And our midline here is 12. So we're going to put 12 is equal to maximum plus minimum all over 2. So we have two equations and two unknowns, maximum and minimum. And we can solve this either by elimination or substitution methods. So let's try to do the first equation in here by multiplying everything in there by 2 so that we can cancel the half. And also the same case for the second equation. So with that, we have now the following. So 8.5 times 2, then that will be 17 is equal to maximum minus minimum. And for the next one, then that will be 24 is equal to maximum plus minimum. As you may see, the right side of the equations actually cancels the over 2 or the fraction 2's in there. And then after this, we can use our elimination method. So using elimination, we can add these two equations. So equation 1 and equation 2, you can add them up. And from adding them up, we can get 17 plus 24. Then that will be well, 7 plus 4 is 11. Carry over 1. Then that will be 41 is equal to twice the maximum. And the minimum values are canceled. And then from here, to get the maximum value, we can simply divide everything by 2. In that case, we can get our maximum value as in this case the 2 over 2 on the right will cancel out, and 41 over 2 can be written as in decimal form as 20.5 in that case. Now using what we call back substitution, in this case, we can back substitute the value of maximum of 20.5 either on equation 1 or equation 2. In this case, I would use equation 2 in that case because I think it's easier to do that. Then from equation 2 in here, then that would be a 24 is equal to maximum, which is 20.5, which is what I'm given already from my elimination method, plus the minimum value. So with that being said, I can subtract both sides by 20.5 to get my minimum value in there. On the right, the 20.5 will cancel out, and I can get the minimum value to be 24.5. No, 24 minus 20.5, which will give me definitely a 3.5 value in there. So there we go. We have our answers now in this case. So the range will have the following. Answer will be the minimum value to be 33.5. That will be, yeah, that will be 3.5 hours up to the maximum value of 20.5 hours. So that does mean that in Alaska for this particular problem, it would get as low as 3.5 hours of sunlight up to a maximum of 20.5 hours of sunlight. You can now use your knowledge of vertical shift and also amplitude and period to know and see in here y equals 17 plus 8 cosine 6 2 theta minus 32 to determine the amplitude and vertical shift, or what we call the midline, for this particular equation or function in there. Once again, let me know if you have questions regarding our midline component, or what we call the vertical shift for our sine or cosine function. And once again, tell me QUAN-do, you QUAN-do math.